In this lecture, we'll continue our discussion on algorithm efficiency, and we'll do this by taking a look at a few more algorithms. Let's take a look at another algorithm which is called selection sort. Now, this algorithm is used to solve another common problem which involves sorting a list of items into some order, whether it's in alphabetical order or increasing order or decreasing order, but we need to take a list of items and sort it in some order. So let's say we have a list of numbers that we want to sort in ascending order in this case. So like for example, maybe I have 5, 7, 2, 8, and 3. That's my current list. Now obviously we're going to sort this into 2, 3, 5, 7, 8. So how do we go about sorting it? Well, we can take our set and partition it into two different sets. So we take our list, partition it into two different sets. One set would be the set of numbers that are already sorted, and then we'll have a second partition or a second set of numbers that are currently not sorted. To make it easier to follow the algorithm, we're going to use a vertical bar to partition our list into the sorted and unsorted sets. So the numbers on the left side of the vertical bar will be the set of unsorted numbers, and the numbers on the right side of the vertical bar will be the sorted set. So what this means is initially our list is going to look something like this, where we have our unsorted stuff on the left side, and our vertical bar is going to be on the far right. Later on, our algorithm is going to look something more like something like this, where 5, 3, and 2 are not sorted yet, so that's going to be on the left side. 7 and 8 are sorted, technically, so they'll be on the right side of the vertical bar. And eventually, our list is going to look something like this, where we have the vertical bar on the far left side, everything to the right is sorted, and we see that we do have a sorted list. Here is our algorithm for selection sort. So the first step is we need to get the values for n and the items in the list. So we need to know how many things are in the list, and we need to know what exactly is in the list. The next step would be to set the marker for the unsorted section to be at the end of the list. So we said in the previous example that the marker, or the vertical bar, we'll call it marker here, is going to be on the far right side initially because the entire list is unsorted. The next step is, as long as there's still something in the unsorted partition, then we need to do a couple steps. So we're going to put a loop in here. In this case, we're going to do steps 4 through 6. So in this unsorted list, we're going to pick the largest number in here, and we're going to swap it or exchange it with the last number in the unsorted section of the list. So when we do that swap, that means that that number plus whatever's to the right of it is now part of the sorted list. So then we would move the marker over to the left one position. And then we just keep repeating that until there's nothing left in the unsorted portion, which means that the marker is going to end up on the far left side. Let's use our earlier example of 5, 7, 2, 8, and 3 to try out this algorithm and see what happens. So the entire list is unsorted, so we need to do that loop portion of the algorithm. The largest unsorted number in this set is 8, and the last number in the unsorted list is 3. So what we're going to do is we're going to swap the 8 and the 3, and then we're going to move the marker over one slot. So that gives us 5, 7, 2, 3, and then we have our marker and then 8. So in this case, 8 is part of the sorted portion, and all the other numbers are part of the unsorted portion. We'll now do the same thing. We'll repeat. So in the unsorted portion, the largest number is 7, and then the last number in the unsorted list is 3. So we're going to swap 7 and 3. We'll move the marker over one slot to the left again, and that gives us 5, 3, 2, the marker, and then 7 and 8. So 7 and 8 are now sorted. 5, 3, and 2 are not sorted. We still have numbers in the unsorted portion, so we're going to repeat the loop again. The largest number in this case is 5. The last number in the unsorted list is 2. So we're going to swap 5 and 2. We'll move the marker over one slot, and that gives us 2, 3, 5, 7, and 8. Now, at this point, we can see that the list is sorted. So, I mean, if we were just looking at it, we could say, all right, we're done. We don't need to do anything else. But the computer doesn't know that. It doesn't see right away that 2 and 3 are technically sorted. It still sees 2 and 3 as the unsorted portion. So we still have to continue with our algorithm, even though we technically already have the sorted list. So In this case, the largest unsorted number is 3. The last number in the unsorted list is also 3. So we simply swap 3 with itself, which isn't really going to do anything. It's just we're going to end up moving the marker over one spot. So we get 2, the marker, then 3, 5, 7, and 8. Once again, we see that the list is technically sorted, but the computer doesn't see that, so we have to continue. So since there's still something in the unsorted portion, we have to follow through. So the largest unsorted number here is 2. The last number in the unsorted list is also 2. It's the same number. So we're going to swap it with itself, which means it really isn't going to do anything. We're going to move the marker over, and now we get the marker, then 2, 3, 5, 7, 8. And at this point, since the unsorted portion is now empty, there's nothing on the left side of the vertical bar, we can say that we're done, that we have a sorted list. Let's see if we can analyze this algorithm and just see how much work is going to be done. So if we're going to do that, that means we need to figure out how much work is done to find the largest number. So what we do here is we're going to compare each number in the unsorted list with the current largest number and update it as we need to. So how many comparisons are we going to need? Well, after the first search, we're going to do n-1 comparisons. Remember, we talked about searching before, and we found that if we have a list of n items, we're going to do n-1 comparisons. So that first time we find the number, and then we move it to the sorted portion of our list. That means that after the second search, we only do n-2 comparisons, not n-1, because once again, we've taken out one number from the unsorted list. We don't need to search the entire list. We only need to search the unsorted portion of the list. So we see there's this trend where every time that we search the unsorted list, the number of comparisons we need decreases by 1. So what's the total number of comparisons? Well, that's going to be n-1 plus n-2 plus n-3, and then we just keep going down all the way to 3, 2, and 1. So this is our total number. Oh, that's great and all, but what does this give us? Well, if we did the entire math, this actually turns out to be a quantity of n-1 over 2n, which comes to 1/2 n squared minus 1/2 n. The question now is, how much space do we need? Well, the original list needed n memory locations, so our input is of size n. We do need some storage to keep track of the marker and where it is to separate the sorted and unsorted portions of the list, and we also need to keep track of the current largest number. So, I mean, it's not much space. It's a very small amount of space when you consider the size of our input. We also need some space for swapping two values, because we said before that we're going to have to do some swapping. In order to do this properly, that means we need to temporarily store one of the numbers before we actually swap the values.